Hello, I'm going to present about some of the work we are doing in the area of dataset and machine learning for power systems. To start off, we would like to bring to your attention this recent perspective article that we wrote together with a group of leading experts on trying to understand the role of artificial intelligence in the era of energy system transition towards low carbon or carbon neutrality. The key premise that we would like to emphasize is that number one, it takes a multi-layered approach to have a true impact of AI in the energy transition. This multi-layered approach needs to span across technology, markets, and policy. Secondly, there needs to have a tight hand-in-hand connection between the domain knowledge of power systems and AI advanced algorithms to improve tangible benefit for the purpose of power system decarbonization. If you think about the overall trend in the area of the electric power grid, digitization has really taken off in the past few decades, and AI or advanced algorithms is one of the three key pillars that really are enabling this fast transition. The other two are equally important, namely the massive amount of data that is becoming available, as well as just the sheer advance in high computing capabilities. And the research community's goal is really trying to take and harness these three pillars of excellence, moving into match with digitization and trying to reduce the carbon footprint, reduce the cost, and improve the reliability of power grid, while in the same time conducting the decarbonization process. It's not easy, but we think it is doable in a use-inspired approach. There are a variety of different use cases that can be thought of by adopting this way of thinking. And let me first just introduce a recent effort that we have been doing on laying the ground for having a common data set for the power grid. This is particularly targeted for a research community that are perhaps beyond traditional power engineering. Research community that are very much familiarized with AI machine learning, but not necessarily so familiarized with the power engineering domain. And one of the unique aspects of the power system is that it is always evolving at multi-time scale, and it is always evolving at bulk transmission level together with the retail distribution level. So how do we create almost an example of ImageNet as they have done for the computer vision domain into a domain of power systems? We have spearheaded these efforts by creating a first of its kind multi-time scale, multi-spatial scale time series data set for machine learning experts in decarbonized energy grid. And in this data set, one can see well-prepared events and normal operating condition data. We also have carefully labeled important events that are of interest in the energy and power domain. And that is the very unique aspect of this data set. In addition to the data set, we have also created a platform that is very much compatible with state-of-the-art AI methods in the context of distribution market simulation. And we call it Open Grid Gym as the inspiration from the work of OpenAI Gym. As the grid is evolving towards more and more decarbonized solutions, massively amount distributed energy resources will be integrated into the grid. And there will be a lot more decision-making coming from the end users. In this case, we call them prosumers because they can have two ways of interacting with the grid. Sometimes being a net consumer, sometimes could be also a net producer. To simulate that, we need to have a platform that is compatible with the existing simulation tools, state-of-the-art simulation tools, and also hopefully could be quick to learn and easy to use by users without too much of domain knowledge of power systems. And we'd like to make it open, scalable, and robust to various market and grid designs. With that in mind, we also recognize that there has been a long tradition of developing such simulation capabilities in the area of electricity market. Some of the notable contributions include software such as MatPower, PandaPower, PowerWorld, and agent-based simulator developed at Iowa State, and so on. So perhaps in light of all these contributions, a few interesting, important contributions that we could point out is that it is compatible with the user-friendly interface with OpenDSS, and it is also very much inspired by OpenAI Gym and sequential agent-based framework, and it's entirely based upon Python, works on any kind of operating systems. And this is the way how we imagine this platform is going to work. We would imagine that there will be state-of-the-art AI algorithms, and there will be high-fidelity retail market simulators. And this Open Grid Gym serves as a bridge to connect these two pieces together so that one can think of ways to evaluating performances and behavior of a lot of new AI machine learning algorithms, for example, multi-agent reinforcement learning. And this is exactly how we define the agent and how the market is defined and how the physics of the grid is defined. And this is the user interface of the flow chart. And then the environment in Python is defined in this way so that the market and the grid are interacting with individual agent through the environment. And that's how you provide a comment to this. And the physical grid is represented as a class. It contains a reset and a step method. And similarly, the market operation is also modeled as a class in Python. And the agent, which are the individual decision makers, are also modeled as a class. And internally, the environment follows a fixed algorithm to update all these three classes of objects, namely the grid, market, and agent. And here is a use case, which is a topology-induced market power. So what we would like to show here is that if there are certain congestion in the distribution grid, a certain expensive generator could potentially exercise market power and raise the prices. And with more demand flexibility, such market power could be mitigated. And this is how the result of the simulation is showing here. And there are many more use cases in the paper. And then to summarize, it provides an open source AI-friendly toolkit for distribution market simulation. And we provided a template for the classes of grid, market, and agent. And it is a great interface with state-of-the-art distribution market simulator, as well as with state-of-the-art AI simulators. And we encourage you to take advantage of this and try it out with your own research. Thank you.